So, well, the talk is about essentially a discrete version of the Yang Baxter equation. And so the first thing that I would like to do is to state which is the main problem that I want to, try to solve. So the problem would be to study the Yang Baxter equation, a discrete version of it. Maybe you don't know which is the Yang Baxter equation, but in any case, I will explain everything. So my goal is the following. So what I want to do essentially is to construct families of solutions, okay? Okay, so first of all, what is the Yang Baxter equation? What is a solution to the Yang Baxter equation? So a solution of the Yang Baxter equation, this is a set theoretical solution, but okay, I will just say solution, is a pair, say XR, where X is a set and R is a map from X cross X into X cross X, which is bijective, and such that, well, it satisfies the Yang Baxter equation, which is this equation that I'm writing here. So of course, I'm using here the well-known leg notation, which means that R1 is R cross identity. So this is a map from X cross X cross X into X cross X cross X. And of course, R2 is identity cross R. So this is the Yang Baxter equation. So here I'm not writing, but here you have composition, right? And this is an equation between functions with domain and codomain in X cross X cross X. Okay, so let me give you some examples first. So examples. So of course, the first example that you might think of is the identity, right? But we don't like this example because we want to use, I mean, what we want to do is to study this from the combinatorial point of view. And of course, you need a definition. What is exactly what you are thinking of if you are saying combinatorial? But well, a very good, say, approximation to answer this would be to try to use group actions. And if you want to use group actions, well, you want to have some bijective maps as part of your map R. So that's why this is not a really, this will not be a nice function, a nice solution. You will understand this maybe later. So the trivial example is the flip map, which is this. This is also a solution, and this is what we are going to consider as the trivial solution, say, over the set X. I can give you more examples. So somehow something similar to this, but a little bit more general. Say that you have two permutations, sigma and tau. So these are bijective maps. And commuting bijective maps. Then this map that I'm writing here is a solution. Okay. This is, well, this family of solutions is known as permutation solutions. Okay. And so I will always use the following convention. So my map R, the first coordinate, of course, depends on X and Y. I'm gonna write this like this. And the second coordinate depends again on X and Y, but I will write this like this, where sigma and sigma of X, sigma sub X and tau sub Y are functions, okay? And as I said, since I want to do this from the combinatorial point of view, I'm gonna put the following definition. We are going to say that the solution is non-degenerate if all these maps and all these maps are bijective for all x, okay? So now, if you do this, then you have groups acting on your set X. And this is precisely what we want to try to do. Very good. And also, I want to consider, so we were going to say that a solution is involutive. Well, of course, if the square of R is the identity. So we are going to work. We work in this talk. I will just consider non-degenerate and involutive and finite solutions. Of course, you don't need to consider only finite solutions, but well, this is something that I would like to do. You don't need to consider involutive solutions, but the theory of involutive solutions is extremely rich, and it is great for a presentation. And well, non-degenerate because I want groups acting on this underlying set. Okay.
What does it mean to be finite?
So finite means that X, the underlying set, is finite. Okay.
Okay. Thank you.
Again, it's something that you don't have to. I mean, of course, if you, in the case of finite solutions, you have more results, right? But well, so as I said, the first say problem, or the first, what I want to do is to construct solutions. Well, you can, with the computer, you can do some experiments and then you can construct solutions. So I can tell you a little bit about how many solutions are there up to isomorphism. So only one solution of size 1, 2 solutions of size 2, 5 solutions of size 3, 4, then 23 solutions of size 4, 88 solutions of size 5. Well, and I can put some more numbers here. Okay. Let me see. This is this. And I can do a little bit more, 2 more. So 9 and 10 here. 9 is this big number. And 10 is this one. Okay. So you have some numbers here. This is the number of involutive solutions, non-degenerate involutive solutions up to isomorphism. From now on, I will just talk about, I will mention, if I say solution, then I'm referring to finite non-degenerate involutive solutions, okay? These calculations were done recently in a paper with Akgon and Martin Merev, using constraint programming methods, okay? Good. So here you have, of course, a problem, an open problem. What about solutions of size 11? So our methods are not good enough for computing all solutions up to isomorphism of size 11. So this is kind of challenging, you know? Very good. So what I want to do? Well, as I said, what I want to do is to construct families of solutions and study them, okay? So the first thing that I would like to do is to use ring theory, non-commutative ring theory, to try to construct a huge family of solutions. And so what I'm going to do is to use radical rings. Radical rings were introduced by Jacobson in the 40s, and say that you start with any ring, R is a ring, then you can always do the following operation, Jacobson circle operation, right? This is the circle operation. And this operation is always associative. And if you do X circle 0, this is the same as 0 circle X, and this is X for all X in R. Okay. And well, we are going to say that R is a radical ring if and only if, this is a definition, R with this circle operation is a group. Of course, there are other characterizations of radical rings, but this is kind of easy to understand, okay? So if you start with any ring, this is always associative with 0 as the neutral element. Of course, this operation is maybe not, you don't have an inverse with respect to this operation, but when you do, then you are talking about radical rings, okay? Very good. So let me see. So let me give you an example of a radical ring. Example. So R is going to be the set of elements of this form, 2x or 2y plus 1, where x and y are integers. Okay. And this is a radical ring because, well, what you need to do is to find the inverse of an element like this. What is the inverse? So this is the notation of the inverse, the typical notation that you do in this theory. This is the inverse of the element with respect to the circle operation. So you can check that this is this. Okay, so, well, so this is a radical ring. Very good. And so why radical rings when you want to study this discrete version of the Yang Baxter equation? Because you have this result of Rump. No, let me put it here. So suppose that you have a radical ring, then the map, so this map, say xy, and here what we do is the following. So I can use the multiplication of the ring, the addition of the ring, and also the circle operation. So, and I can get rid of the multiplication and write everything in terms of the addition and the circle operation, and this is what I'm going to do. So you do this in the first coordinate, and in the second coordinate, you take this element, you consider the inverse with respect of with respect to the circle operation, and then you do this calculation. And if you do this, then this map is, well, a solution, a non-degenerate involutive solution. Okay, so this is a theorem of Rump. Every time you have a radical ring, then you produce a solution. And of course, here you have like, several natural questions can be done, right? Like, for example, do you really need a radical ring, or what is exactly what you need? And this is how we found a new notion, a sort of a generalization of a radical ring, which is called a brace. Okay, and this is the structure that I would like to introduce. So a brace is a triple. Sorry, is a triple. Say that you have A, then you have a plus, and then you have a circle. Where, so the plus and the circle are binary operations on A, and well, it's a triple where this pair is an abelian group. This pair is a group. And of course, as usual, you have a compatibility condition between these two structures. And the compatibility condition is this. So if you do this, well, it's not a distributivity, but sort of something very similar. Is this. And this holds for all A, B, C in A. And this is a brace, right? And okay, this is kind of very funny, but it is not so funny because you have the following examples. So the first example are radical rings. Okay, so every radical ring is a brace. So that's pretty easy. So the theory is clearly non-empty, and it is, well, somehow a spin-off of the classical theory of Jacobson radical rings. And let me give you another concrete example. So say that A is this abelian group written, well, with addition, and then you need to define the circle operation between pairs like this. And what we are going to do is this. So first of all, we take this, and then plus B1 times B2, and here we take B1 plus B2. And you can easily check that this is, again, a brace. Okay, so these are my examples of braces. And why? What can I do with this? Well, I can somehow reproduce the theorem of Rump, right? So theorem, suppose that you have now a brace, then you are going to define a map like this. So, and you use the same formula. So you do this, and then you again do this thing. You take the inverse and then circle A, circle B. Then this is a solution. Remember that solution means non-degenerate involutive solution. Okay, and you can go further. I mean, you can do even further, because it's not that with braces you can produce solutions, but essentially every solution can be produced using a brace. I will mention this later, but I need to explain a little bit more in order to do this. So as usual, let's start with a solution. So non-degenerate involutive solution, finite. Of course, you can define a group. So this is the group with generators in the elements of X and the following relations. So you take XY is the same as UV whenever R sends XY to UV. This object was introduced by Ettinghoff, Scheldler, and Soloviev, and it is known as the structure group of the solution. Okay, and let me compute an example before explaining what you can do with this. So you can say take X as this set, sigma 1, sigma 2, sigma 3. Sorry, this is these two are the identity. Sigma 3 is the permutation 1, 2, the transposition, sending 1 to 2, 2 to 1, and 3 to 3. And tau 1, tau 2, again, these two are the identity. And tau 3 is, again, 1, 2. Well, this is a solution. What is the structure group of this solution? Well, it is the group with generators in X1, X2, X3, say, with these relations. X1 times X3 is X3, X2. X1, X2 is X2, X1. And finally, X2, X3 is X3, X1. Okay, is this group. And you can indeed you have a linear representation of this group. So X1 could be faithful linear representation, could be this matrix, for example. This is a theorem, but okay, just want to illustrate some basic facts. So here, this is X1. X2 is going to be this matrix. Again, you put the identity here. And X3 is gonna be this matrix here. Now you don't put the identity, of course. And then, well, with this, you have that your structure group is isomorphic to a linear group, like this. Okay. So here you have a concrete example of what is this structure group that you have. And let me mention some facts about these structure groups. Facts. The first one is that, well, structure groups are torsion free. There are, I mean, the structure groups have many other properties, but okay, let me mention just that they are torsion free. This was proved by Gateva Ivanova. And Vandenberg. And another fact, which is kind of interesting, is that this is a solvable group. And this was proved by Ettinghoff, Schedler, and Soloviev. Okay, good. So, and the very, very important result here is the following. So suppose that again you start with the non-degenerate involutive finite solution. So then there exists a unique brace structure on the structure group. So essentially what I'm saying is that I can define an addition here in this group in such a way that this is a brace. So this is not only a group, but a brace. And since it is a brace, I can compute the solution associated to a brace. And I can restrict this to X. And this, if I do this, then I recover the original solution. So here I'm using that here, X, so the canonical map that goes from X to the structure group is injected. Which again, this is in general, of course, not true, but in this case, it is true and it is highly non-trivial. But so you prove that the canonical map is injective, and you can also put a brace structure here, a unique one here, in such a way that, well, essentially, the canonical solution that you have over a brace restricted to X is going to be the original solution that you have, okay? And very good. Now, as I said, braces are similar to rings. Remember that, because now it means that in order to study solutions, what you can do is to use ring theory, right? Because braces are generalizations of radical rings. Braces are generalizations of radical rings. And well, so for example, sorry. So essentially you can prove that, so braces with the following properties say that you have the other distributivity. So braces with this, where this distributivity holds, are the same as radical rings. Okay, so essentially what this kind of result tells you that what you can do is to try to use ideas from ring theory here in order to study solutions, right? And this is a very, very, very powerful approach. And well, let's just, I don't want to prove this, but I just tell you that the correspondence is given by the product of the, I mean, in order to define the product to recover the product, you just need to do this. And conversely, right? So essentially, this is how the multiplication, the circle, and the addition interplay. Okay. Very good. So what I want to say now is, well, I mean, I want to show you what can you do with all of this, right? Because so far I did nothing. I mean, I constructed a huge family of solutions using radical rings, but it would be nice maybe to try to understand what you can do. And well, in one of the first papers where set-theoretic solutions were studied, Ettinghoff, Schedler, and Soloviev noted that almost all solutions, at least almost all small solutions, have a very particular shape. Okay, and these are multiple permutation solutions. Multi-permutation solutions. So what is this? Well, this is precisely the following. So you start again with a non-degenerate involutive solution, again finite, and you are going to consider an equivalence relation over the set X. You say that X is related to Y if and only if, and this is the definition, sigma of X is the same as sigma of Y. So you remember that in a solution, you have these sigma maps and you also have the tau maps, but since the solution is involutive, these two are very related, deeply related. So you don't have to consider maybe both of them, but you can just study the sigmas, and this would be enough because of the involutivity, okay? So, and the fact, or the first fact is that, well, this is an equivalence relation. And the second fact, which is also non-trivial and very powerful, is that this equivalence relation induces a solution. So again, non-degenerate involutive solution over the set of classes, equivalence classes. And this is known, this is the retraction, and this is the notation of the solution. Okay, and so under so this is the main definition. We say that the solution is multi-permutation, which means that it is a generalization of the permutation solutions I gave you at the very beginning of the talk. So we say that the solution is multi-permutation if and only if, by definition. Well, so what you can do is retract your solution into something smaller and then do this again and then do this again. And after some steps, a finite number of steps, you get a solution over the set with only one element. So that exists n such that if you apply n retractions to the solution X, then you get just the trivial solution over the set with one element. Okay, so maybe I should write this where, well, this is just applying the retraction several times, right? Good. And well, in order to, I can show you that indeed almost all solutions, small solutions are like this. So let me put n here, multi-permutation solutions, and then not multi-permutation solutions, just some numbers. If you put 5, then you get 84 here and 4 here, 6. You remember that this was the number of solutions, and then 41. If you put 7, then you get this, and then you get this. I don't know. If you put 8, you get. Okay, I can write more, but this should be enough to convince you that almost all solutions are multi-permutation solutions. And it would be nice to understand when these are multiple permutations. So how to characterize this property of being a multi-permutation solution. And I would like to mention the following result. This was done in collaboration with David Bachicher and Ferran Sedó. And well, the theorem says that a solution is multi-permutation solution if and only if And we can do this in terms of the group, the structure group, if this group admits a left ordering. What does it mean? Well, just maybe if you don't know this, well, so we say that a group, so G is left orderable if it admits a total order, say like this, such that it is compatible with left multiplication, meaning that if X is less than Y, then set X is less than set Y for all X, Y, Z in G. And okay, this is a very, I mean, in geometric group theory, it's quite important. In algebra also, it is quite important. And also in topology. So I don't want to give you too many examples of this, but examples. So the first example, say free groups are left orderable, and also the braid groups are left orderable. I mean, these are of course not the only examples, but just to give you a small list of examples. And well, the left orderability of the structure group is equivalent to have this property of having a multi-permutation solution. Okay, very good. I can give you, of course, not all solutions are multi-permutation solutions, but well, and I can give you another result somehow similar, like a technique to let you know when is that you have a multi-permutation solution. Theorem. This was done in collaboration with my student, Emiliano Acri and Rafał Lutowski. So again, you have a solution like this, right? This is your solution, involutive, non-degenerate, and finite, and you can consider a group. So the group generated, this is a different G, right? It's a curly G. The group generated by all the sigma X. This is, of course, a permutation group on X. This is known as the permutation group of the solution. And you have this group. And the theorem says that if the permutation group of the solution, if all CELO subgroups of the permutation group of the solution, which is of course finite because X is finite, are cyclic, then your solution is multi-permutation. Okay, so this is just, I mean, one result that you can find to know, for example, or to detect when you have a multi-permutation solution. And this result is the sort of a corollary of the previous result of this one. Okay, in the proof you need to use this. Good. And well, just let me mention some problem, an open problem here. Problem. So it would be very nice to, I mean, I told you that almost all solutions are multi-permutations, right? But I don't know how to prove that. It would be very nice to have a precise statement and proof of that observation. So for example, this could be this, right? So proving that the number of multi-permutation solutions of size m over the size of solutions of size n, that this limit goes to 1. So this is an open problem. I don't know that, but it would be nice to have this. Okay. So what about the times? Can you tell me how many minutes do I have left?
15 more minutes at least.
15. Okay, very good.
Yeah.
So okay, let me okay, and okay, let me mention a different kind of thing that one can do, again, studying solutions, but now solutions that are indecomposable. So what are indecomposable solutions? Well, again, indecomposable means that you cannot somehow break your solution into smaller solutions, right? But since we are using group theory, it is very nice. I mean, you can define this in a better way using this permutation group, right? So we are going to say that a solution like this is indecomposable if and only if, well, you remember this permutation group on X, it's a group, finite group that it's acting on my solution or on my set X. Well, if this acts transitively on X. So this means that if you take two elements, X and Y in X, then there exists an element G in this group that sends X to Y. Okay, so that the action that you have is transitive. And again, if you take a look at by inspection of the small list of examples, you realize that, well, the number of indecomposable solutions is quite small. Okay, so let me give you some numbers, but very small list of numbers. So for example, here and here, then n is the size of the solution, and this is the number of indecomposable solutions. So for example, if you put 7, then you have only 1. If you put 8, then you have 100. If you put 9, you have 16. And if you put 10, then you have only 36. Okay. And well, several years ago, I think in 2004 or something like this, Gateva-Ivanova made a conjecture that was later proved by Rump. Theorem. Rump proved that if you have a solution with this property, xx is xx for all x, then the solution is decomposable. Okay, this was conjecture by Gateva-Ivanova. And what we did with my students, my student Santiago Ramirez, was to not to generalize, but to find several theorems in this direction. And I would like to mention this quickly. So, so first of all, you can define the diagonal map of a solution. The diagonal of a solution of, say, XR is the map. Say X goes to tau inverse X on X. Okay. And you see, for example, that so if you have this property that you have here, is exactly the same as saying that the diagonal is the identity. Okay, and well, the first theorem that I would like to mention with my student Ramirez is that if the diagonal is a cycle, of course, it's a permutation on X, right? And well, you can indeed, what the only thing you care about this permutation is the decomposition into disjoint cycles. I mean, this is the only thing that it matters. Okay, so if this diagonal is a cycle of length, say the size of X, then the solution is indecomposable. And this is the first result, and another result in the same line, again with my student Ramirez, is that if the diagonal is a cycle of length, say the size of x minus 1, then the solution this time is decomposable. Okay? And well, I mean, this means that, of course, the decomposability is somehow hidden in this diagonal, but it is not clear how to, to find some sort of characterization of the indecomposability in terms of the diagonal, but a lot of information is hidden there. And it would be very, very nice to have all the results in this vein, but of course it's not very easy. So it seems that everything is related to the number of points that are fixed by this diagonal, right? Essentially, I think that there are some conjectures that we have, but well, I don't want to maybe to spend too much time on this, because we don't have really good reasons to believe that this is true. Let me see. So, but again, another problem that I could mention here. So the first one is, well, again, the number of indecomposable solutions is quite small. So maybe the composable of size n, maybe it is possible to prove something like this, and it would be very nice over the number of solutions of size n, that just prove that this is the composable. This is one. Okay, this is one open problem, saying essentially that almost all solutions are decomposable, but it is not clear how this problem is, at the moment at least, it is not clear how this problem is related to all these theorems that we did with Ramirez, or the theorem that Rump proved. Okay, and as I said, okay, let me, I could maybe write this. So the conjecture would be that if the diagonal fixes, say, at least this number of points, then the solution is decomposable. But this is, of course, a conjecture. Okay. Of course, there are no counterexamples in the list of solutions that I show you. But and one more: are there indecomposable solutions where the diagonal is a, say, 3-cycle? Again, of course, this is related to the previous problem, but okay, maybe one can start here, right? Or something like this. Well, I think that this is essentially what I wanted to say. Thank you.
Okay, let's thank the speaker. Are there any questions, comments?
Yes, please, I would like to ask a question.
Yes.
So on the last part, I didn't really get the diagonal. So I understand that this is the related to the diagonal of x times x. But how do you use it as a permutation? This is what I didn't.
Well, this map is bijective. This is something that you have to prove, of course. yeah, sorry, I think I forgot to mention that, but this map that you define is indeed bijective, so it is a permutation.
The
Right?
R,
This is like the, sorry?
the R is, or
No, the R is bijective, but the map
yes.
that I found, that I described, this map that sends X to tau inverse X on X, this map is indeed a permutation, is bijective.
Okay.
Okay, yeah, I forgot
yeah,
to mention
thank you.
that, but yes, this is a permutation. And
Yeah.
so that's why you can decompose this as a product of these joint cycles, and then you can use this cycle decomposition in order to make some statements or something.
Yeah, thank you.
Okay, any more questions?
Okay, maybe I can not ask, but add something close to the subject. First, thank you, Leandro, for the interesting talk. And it's just, okay, maybe comments. So as I know, there are a lot of interesting things which are behind this thing. I mean, regular subgroups of the holomorph, Hopf-Galois extensions, and okay, this stuff. And also very fresh results of Caranti del Corsa about so-called gamma functions, and the results of Valery Bardakov and me about so-called Roto-Baxter groups, which are all of this. Okay, all of them are connected with set-theoretical solutions to Yang Baxter equation, and also braces and skew left braces, and also, okay, we promote some kind of construction and found some sense in which this non-abelian case of skew left braces may be embedded in ordinary groups with some special map. And so some stuff, some definitions may be okay, transferred through this, okay, what we know about groups like solvability, nilpotency, and so on. Okay, it was some remark. Okay.
Okay. Thank you. Yeah.
Okay, any more questions? Okay, then let's thank all speakers again. And I guess we can end here for today.
Okay, thank you.